Right. Hello, everybody. So today we're talking about trigonometric substitution. So the question that we have in this section is going to be, how do we handle an integral like, and then I'll write here, the integral of the square root of a squared minus x squared dx. Okay. So far we haven't learned any tools for how to deal with these types of integrals. So that's what we're trying to do in this section. So what we do in this instance, and let me use a different color here, is we actually say let x equals a sine theta. Right? So that's what we're doing in this section. We take x and we say, well, we're going to replace it with something. So it's called trigonometric substitution. So we replace x with, in this case, a sine of theta. And don't worry, we'll have a list of formulas for knowing what exactly we need to substitute. But just know that in this case, we're going to pick a sine theta, right? So we're gonna know what to substitute in each case, but I'm just going to say in this case, this is what we're going to substitute, and we'll talk about the other cases in a second. So if we see something like this, we just substitute it with a sine theta, and right whenever we're doing u substitution, or in this case, we're substituting x with a sine theta, we need to, of course, also change the variable of integration. So we're changing this into thetas, so we also need to change dx. So what we do here is we take the derivative of both sides, and the derivative of the right side is going to be a sine theta that's not what I meant to write, a cosine theta d theta. Right, the derivative of sine is cosine, so dx by d theta would be a cosine theta, and I've moved the d theta to the other side. Okay, so now we can try to solve this integral just by using this information here. Okay, so if we just directly substitute in what we've written there, then we can say that this is equal to the integral of the square root of a squared minus, well, we plug in x, so x was a sine theta squared, and then dx, we said we replace that with a cosine theta d theta. Okay, so that's what we get there. Let me box this off, and we can go ahead and try to simplify this inside part a little bit more. So we've got the integral of the square root of a squared minus a squared sine squared theta times a cosine theta d theta. And notice in here we can actually factor out a squared, so I'm going to do that. So we're going to have, this is, so let me also factor out this a, right? There's an a here, so I'm going to factor out the a times the integral of the square root. We factor out the a squared on the inside. And this is what we get, right? So I factored out this a into the front, and I factored out a squared on the inside of the square root. Okay, and now we look at 1 minus sine squared theta, and we think, well, we already learned a trigonometric identity that looks a lot like this, namely sine squared theta plus cosine squared theta equals 1. So if we subtract sine squared theta from both sides, then cosine squared theta equals 1 minus sine squared theta. Right? So we can just replace this 1 minus sine squared theta with cosine squared theta. So we're going to do that. And this is going to be a times the integral of the square root of a squared cosine squared theta times cosine theta d theta. Okay. And now we can take our square root, so we're going to get this is going to give us an a, and I'm going to factor that out. So we're going to get a squared integral, or let me just write this in two separate steps. So we get a times the integral of a cosine theta times cosine theta d theta, which is the same thing as a squared integral of cosine squared theta d theta. Okay. Right. So this is our integral here, and now we're trying to take the integral of cosine squared theta. We don't quite know how to do that, so that's an issue. But remember, we also have other trigonometric identities, namely the half-angle formulas. So in this instance, we're going to find something to replace this cosine squared theta with. And using the half-angle formulas, this is actually going to be equal to 1/2 of 1 plus cosine of 2 theta d theta. And notice here that we actually know how to solve this integral. I forgot a parenthesis here. But we actually know how to solve this integral, right? So we distribute, either factor out the 1/2 or we distribute the 1/2. Either way, we get rid of the 1/2. And then we just break it up into two integrals. So we take the integral of 1, that's just theta, and then plus the integral of cosine of 2 theta. Well, you just use u substitution there to take your integral. So I can say here, now we can solve from here. Right, so now we've gotten to a point where we can actually solve the integral. So the idea for this section is we take this thing that we don't know how to solve, this integral, we rewrite it in this form by substituting using this trigonometric equation here. We substitute it, we use an identity. Here we replace this with cosine squared theta, and then here we might have to use another identity. So here we replace this with this, and now we can actually solve the problem. So you may be wondering, how do we know that these are specifically the identities we need to use, and specifically, how do we know that x is equal to a sine of theta here? So I'll write here, so this whole thing is called inverse substitution. And what I wrote down here is just a table of how we know what to substitute and when to substitute it, right? So if our expression contains this type of square root, then we know that x is equal to a sine theta. If it contains this type of square root, it's a tangent of theta. And if it contains this contains this type of square root, it's a secant of theta. So now we can actually just go ahead and solve problems just using this table, and it tells us here exactly which identities we're going to have to use in the problem to help us solve it. Okay, so let's just try to do an example here. So example number 1. I'm just going to say we have the integral of 1 over x squared times the square root of x squared plus 4 dx. Okay. So this is the integral that we're trying to take. And then we analyze, well, we can't solve this integral normally because we don't know how to take the square root of x squared plus 4. So we just don't know really how to take this integral, so we have to use the methods we're learning in this section to replace this a squared plus x squared, the square root of that, and then replace x with a tangent of theta. So we just read the table, and that's what we get, is a tangent of theta. So from the table, well, first we need to figure out what a is, right? So here we're going to say, here, so we've got x squared plus, this would be 2 squared. So here a is actually equal to 2, not 4, right? Because it's a squared is 4, so a is actually going to be 2. So that's important to note. But here from the table, we're going to get that x equals 2 times tangent of theta, right? Again, we had to figure out what a was by saying a squared is 4, therefore a is 2. Okay, so x is equal to 2 tangent of theta. We just get that from the table. and then we take the derivative of both sides. Dx equals the derivative of this side, which is going to be 2 secant squared theta d theta. Okay. And then lastly, well, we have up here x squared. So we have x here. Up here we have x squared. I'll just write here what x squared is equal to. You just square this thing. So 2 tangent theta times itself is going to give us 4 tangent squared theta. Right? So now we can just replace everything in this integral. So that's what I'm going to do. So if we go ahead and replace everything in this integral, then we're going to get the integral of 1 over x squared we replace with 4 tangent squared theta. And the square root thing, we said we can replace this x squared with 4 tangent squared theta. And then we replace, or we just rewrite the plus 4. And dx we said becomes times 2 secant squared theta d theta. Okay, so this is what we've replaced our integral with. And you may say, well, this looks significantly more complicated, but we're just going to work with this a bit, and eventually we'll use this trigonometric identity it said to use in order to simplify this down a little bit. So notice here that we can rewrite this as, so I'm going to rewrite this as 2 secant squared theta over 4 tangent squared theta. Right, so I've just pulled this part into the numerator of the fraction. Notice here, inside of the square root, we can replace this, and we can just factor out 4. So what we're going to do is factor out the 4 times tangent squared theta plus 1 d theta. Okay. So now this is the integral that we're trying to take. And we see, well, tangent squared theta plus 1, it says to use that is equal to secant squared. So we'll do that. So we got the integral of 2 secant squared theta over 4 tangent squared theta times the square root of 4 times we replace this inside part with secant squared theta. Right, d theta. And from here, we're just going to try to solve this, right? So here we take the square root of secant squared, that's just secant. So we can rewrite this as the integral of 2 secant squared theta over, this is 4 tangent squared theta times the square root of this, which is going to be times 2 secant theta, d theta. And we can rewrite that as the integral of 2 secant theta over, so I'm just canceling one of the copies of secant. So 2 secant theta over 4, or sorry, not 4, 8. Eight times tangent squared theta d theta. Okay. And now this looks a little bit complicated, but what we can do is just rewrite everything in terms of sine and cosine, right? So secant theta was 1 over cosine. So we can rewrite this as the integral of 2 over cosine theta over 8 sine theta, sine squared theta over cosine squared theta, d theta. Right? So I just replaced everything with sines and cosines. Tangent squared becomes sine squared over cosine squared. Notice we can multiply both sides of the big fraction by cosine squared theta to get rid of the small fractions. So if we do that, then we're going to get the integral of, so 2 divided by 8, that's 1 over 4, so I'll just rewrite that. But multiply both sides by cosine squared, you're going to get cosine theta over sine squared theta, and this is a 4 d theta, right? So just multiplying both sides by cosine squared, That's what you get. And then 2 divided by 8 is the same thing as 1 over 4. Okay. So now what we have to do is say, well, let's try to think about how we can solve this integral. And you might want to pause and think about how we would solve this integral. Notice first we can factor out this 1/4. So we'll just write that out in front. Right, so we got 1/4 times this integral. And just think about how we would solve this. And the answer here, the first thing we always want to try, other than just solving the integral directly, is of course u substitution. So if we try our u substitution, well, the inside function here would probably have to be sine theta. Then du equals cosine theta d theta. And you see up here we do have cosine theta d theta, so we can try replacing this. This is going to become 1/4 times the integral of 1 over u squared du, right? Because this cosine theta d theta just becomes, sorry, this was supposed to be du. Then we take our integral, we get 1/4 times, right, so this is the integral of u to the -2 du. We take our integral, and we're going to get 1/4, we add 1 to that number, so u to the -1 over -1 plus c. Okay. U to the -1 is the same thing as 1 over u, so we're going to get -1 over 4u plus c. And u, we said, was sine theta, so we get -1 over 4 sine theta plus c, which is the same thing as -1, or sorry, it's -1/4 cosecant theta plus c. Alright, so that looks like our final answer. And you have to look at it and say, well, our original integral was something with x's in it, and our answer here is something with a theta in it, right? So there's some kind of mismatch there. So we need to fix that. So that's the last step of the problem, is fixing the fact that this answer is in terms of theta, but our original problem was in terms of x. So we use this table to get us up to this point, and now we need to use a little bit of trigonometry in order to figure out what cosecant of theta is equal to. So I'll just rewrite a little bit of what we were doing on the next board. Okay, so I'll just rewrite here that our integral was the integral of 1 over x squared square root of x squared plus 4 dx. I know that here we said x equals 2 tangent theta, and we got that this was equal to 1 over 4 times cosecant, sorry, let me rewrite that. That's cosecant theta, not d theta, and then to write plus c. Okay. Right. So now we need to replace this cosecant theta somehow. And the way we're going to use that, or do that, is via triangles, right? So this here means that tangent theta equals x over 2. And if you remember, we have a saying in trigonometry, or an acronym rather. Our acronym in trigonometry was SO, CA, TOA. And what that means is sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So this tangent theta is the opposite side over the adjacent side. So what that means here is we draw a right triangle, where this is our angle theta, and we say that this is the opposite side, x, over the adjacent side, 2. Right? So the opposite side to theta is x, and the adjacent side to theta is 2. So that we can actually now find out what this hypotenuse is. So that's the next step, is to figure out what the hypotenuse has to be. We can use the fact that a squared plus b squared equals c squared. So if we do that, then we're going to get x squared plus 2 squared, which is 4, equals whatever this hypotenuse is squared. And then now we're trying to find c, so we just take the square root of both sides. So c is the square root of x squared plus 4. Right, so we can write that here. Square root of x squared plus 4. Okay, right. So you may be saying, how does this actually help us, right? We've gotten this triangle, but what's actually useful there? And the useful part is the fact that we're trying to find cosecant of theta, but that's 1 over sine of theta, right? So cosecant theta equals 1 over sine theta, which is 1 over, so we said sine is opposite over hypotenuse. So opposite over hypotenuse. And we're taking 1 over that. So that's actually, so 1 over opposite over hypotenuse, that's the same thing as hypotenuse over opposite. Right, so hypotenuse over opposite is going to give us whatever cosecant theta is. Now, we can actually just substitute cosecant theta with whatever this ends up being. So the hypotenuse we said was that. So hypotenuse is square root of x squared plus 4. And the side opposite to theta was x. So now we can just substitute that directly into what we have up here, right? So this was just our scratch work. And now up here we say, well, we have 1/4 times cosecant theta. We replace that with this. So this is times, this would be square root of x squared plus 4 over x plus our constant c. That would actually be our answer there. I think I missed, oh yes, sorry. Sorry, let me just point this out. On the previous page I missed this minus sign here. So if we actually copy that minus sign down, I just forgot to copy that down here. If we just copy that minus sign down, then this was actually negative, but this would be the answer here. Right. So it might seem a little bit confusing just because we've only done one example, but it's actually the same steps for each of the problems. It just, we use different parts of the table for each of the problems, but it's the same steps where you do all of, let me flip over to the other side. You do all of this work where you're taking your original integral, you're writing everything in terms of theta, you're using that trigonometric identity to get everything in terms of theta, and you're just trying to work it until you get a final answer here that's in terms of theta, and then your last step is to turn this answer in terms of theta into an answer in terms of x, which is what we did on the other board right here. So we took our answer in terms of theta, and we said, well, we can do this work with this right triangle to turn it into an answer in terms of x. Okay. So let's do another example here, because these end up being tricky problems. Or maybe not tricky problems, but I mean, if you do enough of them, they're not too tricky, but they do end up being long problems. So let me erase this. So in the last problem we used the second part of the table here. But let's see what we're going to use for this next problem. So number 2 is the integral of x squared minus 1. We take the square root of that, and then we're going to divide this by x to the 4th dx. Okay. So now this is the integral that we're trying to take. Notice again here we've got the form x squared minus a squared. So we're going to use this third part of the table here. So the third part of the table says to use x equals a secant theta. So let's do that. But here we've got to figure out what a is equal to, right? So we take the square root of whatever this is, but the square root of 1 is just 1. So actually, instead of writing a secant theta, I should write 1 secant theta, which is the same thing as secant theta, right? So you got to figure out what a is. But here, a is 1 because 1 squared is, again, going to give us 1. Okay. So this was our x. We take the derivative of both sides. The derivative of secant theta we said was secant theta times the tangent of theta d theta, right? So you're going to need to remember that the derivative of secant is going to be secant times tangent. Okay. And then in this equation we have x to the 4th, so that would just mean that you raise this to the power of 4. So x to the 4th, for example, would be equal to secant to the 4th power of theta. And then x squared is secant squared of theta. Okay, so we just substitute everything in. So using this information, we're going to have that the integral of this is equal to the integral of the square root of, we said x squared would be secant squared theta minus 1 over x to the 4th was secant to the 4th of theta, and then dx we said becomes times secant theta tangent theta d theta. Okay, so now we've rewritten this whole integral in terms of thetas, and now we just need to, our whole goal is just to simplify this thing further. The first step is we look at the table. It tells us to use this identity, and we actually see that right here, right? So secant squared theta minus 1, we can replace that. That's what it says to do. So we're going to do that. So we've got the integral of square root of tangent squared theta over secant to the 4th of theta times secant theta tangent theta d theta. Okay. And now the square root of tangent squared is just tangent, so we can write that. So we've got the integral of tangent theta times secant theta times tangent theta over secant to the 4th of theta d theta, right? So I took the square root of tangent theta, that's tangent theta. I brought this stuff into the numerator, and then that's d theta. Okay. Now we can cancel out one of the copies of secant. So if I do that, we're going to get the integral of tangent squared theta over, so it's secant divided by secant to the 4th, that's going to be secant cubed theta and d theta. Okay. So now we got to do tangent squared divided by secant cubed. And that looks kind of complicated, but what we do again is just rewrite this in terms of sines and cosines. So we can rewrite this as the integral of, so tangent is the same thing as sine theta over cosine theta squared over secant is 1 over cosine theta cubed d theta. Okay. Right, so I just replaced those, and now we can just multiply everything out. So if you square the numerator, you're going to get sine squared theta over cosine squared theta. And then if you square the denominator, or sorry, not square, if you cube the denominator, you're going to get 1 over cosine cubed of theta d theta. Right? And then you've got to analyze, how do we get rid of these fractions, right? So we've got fractions inside of fractions, which is never a good thing. So we want to get rid of the small fractions. And you want to look at, so you might want to pause the video, think about how you would do that. But the way that I would do that is just multiply both sides by cosine cubed theta, because if you multiply the denominator by that, that cancels out. and then you just multiply the numerator by that. So if we multiply, and I'll write here what I'm doing. I'm going to multiply this by cosine cubed theta, and I'm going to multiply this by cosine cubed theta. I'm doing the same thing to both the top and the bottom of the fraction, so it doesn't change anything because they just cancel out, right? So we're maintaining the fact that this is the same fraction, because I'm just multiplying the numerator and denominator by the same thing. But now, cosine cubed divided by cosine cubed, that's going to cancel out. Let me say that cancels out. And now we just got to have this numerator. We've got to work on that. So this is going to be equal to, so cosine cubed divided by cosine squared, that's just going to leave us with one copy of cosine. So we've got sine squared theta times cosine theta d theta. Okay, so you can see how rewriting this whole thing in terms of sines and cosines helped us out quite a bit. Okay, and now I can try and see and pause the video here to think of how you would solve this integral, but again, we just use u substitution. So we say u equals sine theta, because that's the thing that's being squared. Then du is cosine theta d theta. So we can replace this. Let me write here, this part is u squared, and this part here is getting replaced with du. Right? So if you look at the work we did here, that matches up with this. And now let me give myself a little bit more space here. We're going to get the integral of u squared du, which is u cubed over 3 plus c. And then you just had to replace what u was, so u was sine theta. So we get sine theta, so sine cubed of theta over 3 plus a constant c. Okay, and that looks like our final answer, but again, this is in terms of theta. Our original thing was in terms of x, so we've got to rewrite this sine theta with something in terms of x. And again, we're going to use that triangle to help us do that. So let me rewrite what we had on the other side. Let me first erase this. Right, so we had the integral of square root of x squared plus 1 over x to the 4th dx, and we said that that was going to be equal, so what we did here was we set x equal to b secant theta, and we said that that was equal to sine cubed theta over 3 plus c. Okay, so I just rewrote down what we had on the other board. We had this integral, we did a bunch of work to get to here, and this is what we set x equal to. That's the information we need. Okay, and again, we need to go ahead and look at, well, secant is 1 over cosine, so x equals 1 over cosine theta. We're trying to solve for cosine theta, so we multiply both sides by that. Cosine theta times x equals 1, and then we need cosine theta by itself, so we get cosine theta equals 1 over x. So the point of that, again, is using our acronym SO, CA, TOA. Cosine is adjacent over hypotenuse. So this is the adjacent side over the hypotenuse. So if we draw our triangle again, this is our right angle, this is the angle theta, and we said the adjacent side to theta is 1, and the hypotenuse is x. And now we're left solving for this side here. So a squared plus b squared is c squared. And we know a is 1. So 1 squared is just 1. We don't know what b is, but we know that c is x. Sorry, c squared. Or yeah, sorry. Getting mixed up here. But the side c is x, so you've got to square that, right? So the side a is 1, a squared is 1 again. And then, sorry, this was b squared. So 1 squared plus b squared equals x squared. Got a little muddled in my wording there, but 1 squared plus b squared is x squared. That's just from reading the triangle. This side is b. Right, now we've got to solve for what b is equal to. So b squared is x squared minus, well, 1 squared is 1, so minus 1. And then you take the square root of each side. So b equals the square root of x squared minus 1. So instead of b here, I'm going to replace this with the square root of x squared minus 1. Okay. So now we've solved for all sides of the triangle. Now we can actually figure out what sine of theta is equal to. That's our last part here. So sine theta is equal to, we use our acronym, opposite over hypotenuse. And we know the side opposite to theta is square root of x squared minus 1. And we know the side adjacent, or sorry, not adjacent, it's opposite over hypotenuse, so the side that's the hypotenuse is x. So we can replace sine theta exactly with this expression. So we know sine theta is being cubed, so we'll replace it with 1/3 of this fraction cubed plus c. Okay, so that's going to be our final answer. So once again, let me just go over the steps to this problem. So we started here. This was our integral. We looked at the table. We know we have the form x squared minus a squared. So we use this part of the table. So we use the third row here. And we say, well, that tells us that x is going to be a, which in this case is 1, times secant theta. We just substitute that. We use our identities to get down to this point. And then we just do a u substitution to get to here. And now we've got our answer, except it has theta in it instead of x. So we need to figure out what sine theta is equal to. So we use, in order to figure that out, we just use what we set x to be equal to. We reverse engineer that to say, well, cosine theta is 1 over x, which is the same thing as adjacent over hypotenuse. We then use this triangle to figure out what sine theta is equal to. And then we plug in what sine theta is equal to. Okay, so again, pretty long problem. So I'm just going to do one more of these. All right. So the third and final problem that we're doing here today is this problem, and we look at the integral and we say, well, we can't solve that normally. We can't solve it using u substitution. So now we try trigonometric substitution. So we look at this 9 minus x squared, and we see it matches this form up here in the first row. So we know using this first row that we need to set x equal to a sine theta, but if we figure out what a is, it's going to be the square root of this number. So it's the square root of 9, which is 3 times sine theta. Okay, so that gives us x. Now we take the derivative of both sides. Dx is 3 cosine theta d theta. And now, well, here we have x squared in the problem, so I'll just write down here. You don't have to do this, but x squared is 9 sine squared theta. So I just squared x, and that's what you get. Okay, and now we can go ahead and rewrite our integral in terms of theta. So if we do that, we're going to have the integral of x squared, we replace that with this, 9 sine squared theta. And then the square root of this term, we said, well, here we've got the square root of 9 minus, well, x squared we replaced with 9 sine squared theta. And now here, this dx we replaced with 3 cosine theta d theta. Okay, so it's important to remember that we're not just replacing dx with d theta, we have to replace it with whatever we found here. So here we found 3 cosine theta d theta, so that's what I replaced it with here. Okay, and now we just need to simplify this a little bit. So I'll go ahead and say, well, and it says we need to use this identity, so we want to try to use that identity, so we can go ahead and say here, so I just brought the second part into the numerator. But in the denominator, what I'm going to do is factor out this 9. Because once I do that, you can see that we can actually use this identity in the problem to replace this 1 minus sine squared with cosine squared theta. So if we do that, we're going to get the integral of, so 9 times 3, that's going to be 27. Sine squared theta, cosine theta, over the square root of 9 cosine squared theta. Okay, so this is what we get, d theta. Sorry, I forgot to write that part. Right, so this is what we get. And now we just need to solve this. So the square root of 9 cosine squared theta, we can take that square root. So we're going to get the integral, let me factor out 27. So we're going to get 27 times the integral of sine squared theta, cosine theta, over this denominator, which is going to become 3 cosine theta, d theta. Okay. And now we can go ahead and, well, let's factor out the 1/3. So we're going to get 9 times the integral. The cosines are going to cancel. We're going to get the integral of sine squared theta d theta. And notice we don't quite know how to take that integral. So again, we're going to have to do a substitution. So the formula that we're going to use here is actually one of the half angle formulas to say that this is rather 9 times the integral of 1/2 times 1 minus cosine of 2 theta d theta. Okay, so we just used the substitution because we didn't know how to solve this, so we need to replace it with something else. And notice we don't want to use the fact that sine squared theta is 1 minus cosine squared theta, because that wouldn't actually get us anywhere, because then we'd just be taking the integral of cosine squared theta. That doesn't really help us. So we need to use the half angle formula here. So if we do that, and we go ahead and use substitution to solve this integral, then the answer that we're going to get is, so you would have to do the work here, but it would be 9/2 of theta minus 1/2 of sine theta, sine of 2 theta plus a constant c. Okay. But here we're going to need to figure out exactly what these things are equal to, right? So we need to figure out what theta is, and we need to figure out what sine of 2 theta is, right? So first we want to look ahead and look back and see, well, x is equal to 3 sine of theta. So I'll say here x equals 3 sine theta. That's the information we had there. And now we can solve for sine theta and say that sine theta equals x over 3. And if we remember, it was so ka toa, right? So ka toa says, well, sine is opposite over hypotenuse. Opposite over hypotenuse. So if we draw our triangle, this is theta, then the side opposite to theta is x, and the hypotenuse is 3. So we've just got to solve for the remaining side. This is a. So a squared plus x squared equals 3 squared. Now I just got to solve for a. So a squared equals 9 minus x squared. So a equals the square root of 9 minus x squared. Okay, so we figured out what a is equal to. Okay, so we've done all this work here. And now we need to solve for both theta and sine of 2 theta. So let's write down here that theta, so if we solve for theta here, actually what I meant to write here. So we know that sine theta equals x over 3. So if we do sine inverse on both sides, we know that theta equals sine inverse of x over 3. Right? So I just did sine inverse on both sides of this equation to get to there. So we can actually just replace theta right there with this form right here. And then we've got to figure out what to do with this sine of 2 theta. So this was our first thing. And our second thing here is to say that, well, sine 2 theta, we actually have a formula for what that's equal to. Right? So that's actually equal to 2 sine theta cosine theta. Right? So we can now rewrite this as 9 over 2 times this sine inverse of x over 3 minus this 1/2 of, we said that this was 2 sine theta cosine theta plus c. Right? So now we just need to figure out what sine theta and cosine theta are. Right? So sine theta, actually we already know what that is. It's x over 3. Right? But we need to figure out what cosine theta is. So right here, cosine theta equals, well, we said here with the acronym, it's adjacent over hypotenuse. So the adjacent side to theta, we said was a, which was this. So it's the square root of 9 minus x squared. And the hypotenuse we said was 3. Right, so we get this equation here. And then now we can just try to solve for our integral. So our integral is 9/2 times, we have the sine inverse of x over 3 minus 1/2 of, we said that sine theta was x over 3. And we said that the cosine theta was this fraction. Square root of 9 minus x squared over 3 plus c. Right? And that would be our final answer.